Arima and Sarima, while we have many other models like that. So we are going to take a start from that. Then next, then okay. So what exactly is time series? Now, one of the fundamental thing that I want us to pick is the fact that it is a sequence of data points collected or record at a specific or regular time interval. So another way I can say that it is an observation collected in sequence of time. So that is a key component of time series data is the fact that time is there is it is ordered in time, ordered in time. So we have, for instance, I have a typical example of that here. So time series data can be observed at all levels across areas of risk demand for electricity, and this is collected over minutes. So it could be in minutes, over regular time. You know. So then, what exactly is time series analysis? So time series analysis is the art of extracting meaningful insights from time series data. So I want us to pay attention to the fact that we say we are what? Extracting what? Meaningful insights. So, many times people don't know that many times, just like Prof has always teach us, people always confuse method with how you can use method to address a particular question. So this is a tool to respond to certain questions that could be arising in different applications. It could be in finance, it could be in epidemiology, it could be in climatology and all that. So we are going to see some of this as we proceed. Now, this is done. So how is time series done? So time series is done by exploring the structure and the characteristics of the series. Then it is also very useful in identifying patterns that can be used to forecast future event of the series. So many times when people collect data, we don't know we we um we can't do so much with data except we use a model at least to help us let the data speak. So that is based on the data that we have already, what is going to happen. So that is what a time series can help us with. So that is we can make forecast. Okay. Then we say when forecasting time series data, the aim is to estimate how the sequence of observation will continue into the future. So the future is always unknown. So many times people have questions around this. What will happen? And that is why time series is one of those tools that could respond to questions like that. Are we still together? Are we still together? Are we still together? All right. I need to be. So these are typical example, or I'm just going to take some of them, few of them. So applications of time series, time series analysis is applied in the following. For instance, let's say we have a retail store. A retail store. Certain data are collected over time. So we want to forecast the sales. An important tool that can help such company or help such organization is time series. It could help them forecast sales that they could have, haven't collected certain data over time. Okay. Then also we have energy company can use it to forecast revenues, reserve, production, demand, and prices and stuff like that. So banks could also, quite of important note is meteorologists. They use it to perform monthly for weather forecast. So sometimes they use these tools to make forecasts, particularly when it comes to weather forecasting also as well. Okay, so I've also laid because I want us to see this as a tool that can respond to questions. That is, probably you have a question. How can you, just like Prof has taught us that if you want to start a research, the first thing is you define your problem. So based on the problem that you define, tells you what kind of data will help and also what kind of model you will need. For instance, let's say I have a time series data and I want to make forecast. I know that if I want to make forecast, which is a need that I need, I know that the time series model will be very good for me to make good forecast. Okay, so what are the things, the main goals that a time series analysis will do is description. So that is, it can help me summarize patterns. So questions like, is there seasonality based on data? You know, when you plot a data, there's little you can see about the data, except you start doing some certain analysis that help you extract meaningful information from there. So for instance, let's say I have a count case of cholera or malaria. I want to ask, is there, am I seeing a seasonal seasonality in the data in terms of systematic peak of infection at a certain point in time in the year? So a time series analysis can help me do this. In terms of description, it can summarize pattern. Is there seasonality? Is there a trend? That is there an upward trend or what? Downward trend? So for instance, look at this, an example. Measles peak every March to May in Nigeria. How did they come to that kind of conclusion? Something has been done. So that is based on certain analysis that has been carried out, they could draw out those meaningful insights. So, and these are things that are very useful to people, particularly in the public health space. They need information like this. So what would this kind of information do? So this, if a time series analysis has been done and we know a certain time where certain occurrence is happening, we can be proactive in our interventions, not reactive. As to we already know this window of certain we have of measles cases. So what can we do before the window of where we experience such peak? All right. So then also explanation. Understand drivers. Rainfall explain malaria. Does vaccine explain decline? And all of this. So that is, you can also use time series model, incorporating other variables as an explanation of what exactly could be driving certain. For instance, let's say we have known from literature that there are certain climatic variables that explain malaria incidence in a way. That is, rainfall has an influence on malaria. Okay, then also, aside explanation, forecast. So that is, we want to predict future. What is going to happen in the next 2 weeks? What is going to happen in the next? Those are questions that are always being asked by people in different industry. And time series is such a good tool that can respond to such questions. Are we still together? Are we still together? All right. So then also control intervention, impact of lockdown, vaccination can, that this time series can help you also help us evaluate intervention by using their what we call interrupted time series. So it can help us also look at some of these certain concepts. Okay, let me move fast. So we have different kinds of data. So you can use a time series model on a cross-sectional data. Why? Because it's different. What is a cross-sectional data? That is an observation are from different individuals at a single point in time, a snapshot, just like a survey. So that's a cross-sectional data. It's not, it's just at an instant in time, not changing over time. So what is a time series data? Just like, I'm just going to reiterate that. Set of observation collected for particular individual or entity. It could be malaria case, it could be rainfall, over different time points. Over different time points. So we keep emphasizing the fact that it is ordered in time. Okay? Okay. So in cross-sectional data, the time frame is kept while observations are taken from different individuals, but in time series, we are shifting the time frame over a wide range time for a particular individual or location. So those time series focus on what? The same variable over what? Over a period of time. But while cross-sectional data focus on several what? Variables at a single point in time. Okay. So these are typical example. I might not be able, I'll just pick one or two. Typical example of cross-sectional data. For instance, let's say they are carrying out let's say malaria prevalence rate across Nigerian states in 2021. So That's at a point in time. DHIS data is a kind of study like that. Then also we have time series data. For instance, we have monthly malaria cases in Abuja from 2015 to 2023. You see? So monthly malaria cases from 2015 to 2023. So it is ordered in time. Okay, example, I don't want to, so the example, we have what we call panel or longitudinal data. So these are observations at different cross-section over time. It's a combination of what? Both cross-sectional data and time series data. So an example of that is when we have annual malaria mortality rates of different states in Nigeria between 2015 to 2024. So now, having established what a time series data is, so what are the components that we can extract or components that are inside a time series? Now, number one is what we call, they can be generally decomposed into what we call trend, seasonality, cycles, and residuals, or we call remainder. So what is a trend? A trend exists when there is a long-term increase or decrease in the data. So that is what we call an upward trend or a downward trend. So it gives like a bigger picture. For instance, let's say I'm analyzing sales of data and I observe that there's an upward trend. So it means that could indicate that the business might be what? Growing over time, right? So for instance, what kind of trend is this? Upward trend. So we could also have downward trend. And there are some certain data that possibly there's no really trend. Why? Probably there is changing over time, but there's no clear distinction of trend as to whether it is upward or downward. Okay. So we also have seasonality. It says seasonality refers to the systematic peak that occurs at regular intervals. So seasonality is always of a fixed and known period. So for instance, just like a typical example I give, at what point do we experience certain, is there a systematic peak that occurs at regular interval? So for some diseases, it has been established that at certain period of time in the year, we have, there is a repeated pattern of that. That is, you know that within this window and this window, we have a peak of certain disease cases in that particular location. So now, for instance, example, poultry farmers often see a spike in sales. Okay, this is not even see a spike in sales of chicken during Christmas. Is that true? So it has been observed. So there is seasonality. So stationary stores see increase in sales every September. Is that true? Okay. All right. So then also cyclic. So a cyclic pattern exists when data exhibit rises and fall that are not often of fixed frequency. A cycle occur at irregular intervals. For instance, if the fluctuations are not of a fixed frequency, it's different from seasonality. Regular. This one is what? Irregular. Yeah. So if the fluctuations are not of fixed frequency, then they are what? Cyclic. If the frequency is not fixed and the pattern is seasonal. So for instance, an economy might go through cycles of what? Growth and recession that don't occur at a fixed period. That is very true. So in that kind of case, we call it a cyclic. Then what we call residual or remainder. So remainder or residue are what is left after we have what? After trend and seasonality are removed from the original time series. So residual have no trend or seasonal pattern, so they represent what? Short-term fluctuation. So this is a typical example of that. All right, so now time series decomposition. So we have talked about the component that we can get from a time series data. So why do we do time series decomposition? Is form of what we call exploratory data analysis. We are trying to extract information from the data. For instance, if I have an original time series data, there might be so little I can extract or so little that is visible to see with the eyes. Until I decompose the data into different components, I'll be able to make clear and convincing insight, draw convincing insight and conclusion from that. So time series data decomposition is a process of separating a series from its what? various components. So what are those components? What are those components? We said trend, seasonality, remainder. All right, so the insight gain helps to identify the most appropriate forecasting method to handle what? The series. For instance, if the decomposition shows that the series has a strong seasonal pattern, you should select models that have the ability to handle this pattern. So just like I say that there's what we call a time series modeling work. So when you do this decomposition, it has a way of, you can draw meaningful insight as to describing the data itself, and also it can give you a pointer as to possible or candidate models that might help fit the time series data itself. Okay, talk about this. So now, when it comes to decomposition, we have quite of different kinds of so we have what we call the additive versus the multiplicative models. So additive model assumes that the observed time series is the sum of its components. So that is, you have our observation is equals to what? Trend. Observation is the original time series itself, is equals to what? Trend plus seasonality plus what? The residual. Then the additive models are used when the magnitude of the seasonal and the residual values are independent of trend. That is, the magnitude of the seasonal component roughly remains the same over time. So what about the multiplicative? So this is what we have. You have the original time series. We have trend multiplying what? Seasonality multiplying the residual. So the multiplicative model assumes that the observed time series is the product of its components. So behind every of these models, there are assumptions. There are underlying assumptions. Okay, so multiplicative models are used when the magnitude of the seasonal and the residue value fluctuates with trend. So that is, the trend or the magnitude of the seasonal component increases or decreases by some multiplicity from period to period over time. Okay. It's not moving. Okay. 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 So I want to take a typical example of this. So for instance, we have a time series that has been decomposed. For instance, if you look at this part, we have the what? Observed. Can we see this? From the previous slide. Not moving. Previous slide. Yeah. So this is the original time series data itself. So this is Australian anti-diabetic drug sale. So this is how the time series data looks like. So we want to subject this particular time series data into, we want to decompose it to be able to describe the data itself, to characterize the data itself. Are there irregular patterns? What are the things? What are the meaningful insights we can draw from this particular data? So now look at this, the original data itself. Then it has been decomposed into what? Trend, right? And what? Seasonal, and what? Random, which is also the same for name for residual. So now what can we observe about this based on this decomposition? One of the first things we can see clearly is that there's an upward trend, right? So that is, there's an upward trend in sales of anti-diabetic drug. Then also, can we see seasonality? So at least we see a regular repeated pattern at some point, in a way. Can we? And then we also see the random part of that, is the remaining part of the series. So now, for maybe when we do the hands-on, so most times when we apply some of these things, we use, because of we have quite a number of them that we use for decomposition. So most times we use STL, which is seasonal and trend using Loess, because it's more robust. It gives you the hierarchy of how associated the significance of each of the components to the original series itself. So let's explain some concept in time series itself. So what is lag in time series? So lag refers to what? The past value. Are we still together? All right. So lag in time, lag refers to the past value of a time series used to predict or explain the future value. So it helps capture the temporal dependencies in the data. So that is a lag in time series means shifting the series backward by a certain number of time steps. So if you have a time series y of t, so then the lag is what? Lag 1 is the previous. Just like we have said it is ordered in time. So that is something as a data was collected yesterday, today. So based on what we have, so there is a between today. So that is, if you have a time series y of t, let's say the observation of today, then there's a lag. That is the previous time. Yeah, but so is a new series formed by shifting the original series one backward. So by using the lag function in R, we can generate lag versions of a time series. So for instance, look at this. So this is the date. This is the date. So this is the original time series itself. So these are the lag observed for each of the distance. These are the lags observed. So I need to run fast. So another concept that is very important is correlation. We need correlation because we have something we call ACF, and we have what we call PACF. So we are going to get there. So correlation means what? Association. Correlation means what, everybody? So it is a statistical measure that quantifies the strength and direction of how two variables are related. So for instance, if you look at this, what kind of correlation is this? For this one, positive. This, there's no, obviously there's no correlation while moving around 0. Most likely the correlation coefficient will be 0. Then this is what? Negative. So now we need the concept of correlation to be able to, in terms of the ACF and PACF that we'll discuss. Why? Because we must also know that correlation does not imply what? Causation. What did I say? We are not in this class. We must know that what? Correlation does not what? So that is two variables move together does not mean that one is causing the other. So we must take note of that, please. Let me move fast. So these are just formula we different. I don't want to. So now there's something we call autocorrelation. So this is where I'm coming. This is where we'll be using that. So autocorrelation measures what? How similar a time series is to what? To its lagged version over time. So let me come again. Autocorrelation what? Measure how a time series what? Is to its what? Lagged version over time. So it uses the same time series twice, once in its what? Original form, and once lagged one or more time period. So how similar is today from what? Yesterday. So autocorrelation helps us to look at that. That's a typical example of what that. Okay, this is the. I don't want to bore us with that. So then we have a function, what we call a. So now, what we call ACF, autocorrelation what? Function. So this ACF is a function inbuilt in R. Most likely, what we'll be using to do this in hands-on, the hands-on session will be R majorly. So the ACF functions from the start package is used to what? Visualize what? The result using a bar plot. This is a typical example. When you subject your time series data, you want to check the autocorrelation. So we use the function to plot the correlation of what? The anti-diabetic series and its first 48 lags. So now let's look at this very well, and we are going to make an interpretation from what we are seeing. So this is what the autocorrelation of the anti-diabetic drug is giving us. So he's saying that each bar in the ACF plot represent the level of what? Level of what? Correlation between the time series and its what? Lag in a what? Chronological order. So we are saying that how correct is the lag series from its what? The original series itself. Okay. We're going somewhere. So now from this plot, we have that the blue line indicates whether the level of correlation between the series and each lag is significant or not. it is observed that the correlation of the series with what? Its lag is decaying over what? Over time. Can we see that? See that? This. Over time. If you look at the bar, can we see it now? So we are saying that, look at the bar. That is decaying over what? Is it decaying over time or is increasing over time? So also, the closer the lag is chronologically to the series, the relationship what? With the what? With the series. So now, I haven't carried out autocorrelation. So there's what we call the partial autocorrelation function, which is called PACF. And it has what it does. So when calculating the correlation of the time series with K lag, now ACF does not remove the effect of the lag one. So what does PACF itself measures? So PACF measures the direct correlation between the time series and its lag value after controlling the effect of the immediate lag. So PACF removes the indirect effect of preceding lags and show true direct relationship. So these are concepts that is very important. So now the PACF function is used to what? Visualize the result we have here. So this is the PACF. Okay, thank you. So this is the PACF. Also measuring correlation. So now another concept that I would like to introduce is when we say if a time series data is stationary or not. Now we have stationary data and we have non-stationary data. So when do we say that a time series data is stationary? What does it mean when we say a data is stationary? It's a statistical property to say that the data is what? Is stable over time, right? Are we still together? Are we still together? Okay. So so a time series data is said to be stationary if its statistical property does not what? Change over time. So more precisely, a time series is stationary when the mean is what? Is constant over time, and when the variance is also what? Constant over time. So now, in general, a stationary time series will have no predictable pattern in the long term. So time plot will show the series to be roughly horizontal with constant variance. So a time series that is not stationary is said to be non-stationary. Now, where we will be using this is that there are some of the time series models that we have that some of the underlying assumption is behind whether it is stationary or not. So there are some time series models that you can deploy or build and implement that you must ensure or check that your time series itself is stationary. If it is stationary, you can use such models like ARIMA and SARIMA. So it's a property that must be checked. So is the data stationary? So if the data is not stationary, what do we do? So we have what we do to do such data. So but how do we check for stationary itself? So very fast, okay. It's not moving. Okay, so how do we check for stationarity itself? Now we have aside visual inspection, what we are saying is that the variance is the mean is not changing over time and the variance is not also what? Changing over time, right? So look at this now. Obviously, this is changing over time, yes or no? But if you look at this version of the moon, is it changing over time? So there's difference between this and this, right? So that is to explain the concept of stationarity. All right. So another way we can check for stationarity is when we look at the ACF plot, then we look at what when we look at the ACF plot. Another way we can do that is also when we carry out statistical tests. One of them is what we call the augmented Dickey-Fuller test. So how do we carry that out? When we subject the data, we are checking for stationarity as to is the mean and the variance changing over time. So when we subject that to the ADF test, so what is the p-value? If the p-value is less than 0.05, what does that mean? Okay, So that is now, so if we have such, so after carrying out the test and we see that the p value of the time series is less than 0.05, we accept, is it accept now, accept the null hypothesis to be what? That is stationary. So now, these are other tests that we can use, KPSS test to check for stationarity test. So we can also explore some of these, but much more, I use this more often, the ADF test. So, all right, so let's move. Now, another way we address, say, one of the ways we address stationarity is when we observe, for instance, after carrying out our ADF test, observe that is stationary, is non-stationary. So what do? We do what we call differencing. What did I call it? Did I call it? All right. So what is differencing? It means what we are doing is we are so differencing is one of the most common techniques of making time series what? Stationary. So differencing can help stabilize the mean of the time series by removing the what? Changes in the level of the time series and therefore eliminating trend and seasonality. So it means you are removing the what? The present from the past, just like that. You are differencing. So then you get another set of series. Are we together? Are we together? All right. So that is what differencing does. So look at, for instance, let's look at this particular time series data. So this has been transformed. What has been done to this? It has been log transformed. So that is, there's a transformation that has occurred to this particular data. And one of the reasons why we do transformation particularly also is to see how, if we transform the data, can we also observe the property of stationarity? Will it be stationary? Okay, so after differencing, we have this. Can we observe the difference between the two now? This is the log version of the original time series in itself, and this is after differencing has been done. So can we say that this data is stationary by just visual inspection? Can we say? Why? 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 Okay, I have to. So now, one thing we can observe is that both the mean and the variance are constant over what? Over time. Okay, so I need to run along. So now, some of these concepts that I've mentioned are going to be very useful in our what? Forecasting models. I told us that one of the usefulness of time series is to make forecast, which is questions many people need answers for. So now we have autoregressive models, what we call AR models. We have moving average models. So which some of these properties must be in place before we can use some of these models. Why there are some models that you don't necessarily need to check for the stationarity for you to know whether it is what, for you to be able to use those models. But autoregressive models, moving average, ARIMA, you must satisfy the property of what? Stationarity for us to be able to use those models. So those are the underlying assumptions that must be met. Are we together? Are we still together? Are we still together? All right. So this is for ARMA. So ARMA means it's a combination of what? Autoregressive and also the moving average. So I have to run a bit fast because of my time. So now ARIMA is the difference is we have it is more like a upgraded version of ARMA because you have what we call I in the middle of ARMA, which is ARIMA. So which means integrated, and it helps in terms of that means you are differencing the data to satisfy the property of stationarity. So ARIMA is a combination of what? Autoregressive and moving average. Then you have integrated ahead. So it's a combination of, so that is one of the limitation of AR, MA, and ARMA model is that they cannot handle what? Non-stationary what? They cannot handle what? Non-stationary what? Time series data. So to use ARIMA, so which in a way suffice the high def means you have difference the data, which helps satisfy the property of stationarity. So which is building on that limitation of those models. Okay, I have to run fast. So now, for instance, one of the important things I need us to know, particularly for ARIMA model, is the fact that there are some parameters in the model. We have what we call P, D, and Q. So what is P? P is the order of the autoregressive part, and D is the what? The degree of differences that was involved. Do I have to difference it 1 or 2 times before I can achieve the property of stationarity? Then also the Q part is the order of the what? The moving average. Just like we know that autoregressive itself is a model, moving average itself is a model. So a combination of that, building on the limitation of all the models, is what ARIMA is doing for us. Okay, so these are PDQ are major parameters that are useful for us to be able to deploy or implement ARIMA. So then we have another type of that, which is what we call, somebody was correcting me, is SARIMA. Before I used to call it SARIMA. So SARIMA, which means seasonal ARIMA. So that is in this one now, this kind of model handles data where you have observed strong seasonality. An example, inside ARIMA and SARIMA, ARIMA and SARIMA, which one do we think will fit better for a malaria data? Why? Because SARIMA, right? Because there's a seasonal pattern that is observed, particularly with respect to malaria data. Okay. So now for that, we have the small letter PDQ accounting for the ARIMA part, and for the seasonal part of the model, we have the what? The capital one accounting. So this is the seasonal component, also catering for the order of the what? The AR, the differencing, the what? The Q is for the what? The moving average. Then S there is the what? Is the seasonality length. So depending on the kind of data I'm analyzing, probably is a yearly data or a monthly data. So if it's a monthly data, the period I'll be using will be 12 because I have 12 what? 12 months in a year. Or let's say we have weekly data. So how many weeks do we have in a year? 52. So that form informs my period, my S. Okay. All right. So these are hands-on that we are going to try. Some of these things are things we are going to try with our hands in the next class. So I don't want to. So I've explained some of them where you check for stationarity and you reject type if it is stationary or not. So then for these are visuals for ACF and PACF. All right. So now forecasting with ARIMA. Now, one of the things I need to say to us is that we must have candidate models that we are deploying, that we are fitting our model to, candidate models that we are fitting our data to. So that is, for instance, I can have quite a number of them. Let's say I have five. So, and if you observe, for each of the model, the orders will be different. You see, for instance, for this ARIMA, and for this a model selection has been carried out already, and based on that, they chose this to make forecast. You see that we have ARIMA 311. So what is the order of what is 3? 3. The order of what? The okay, I'll round up. The order of the what? The AR part, right? The autoregressive part, right? Then how many times do I have to difference this data? 1. Then the one there is what? The order of what? The moving average. So now, I haven't have candidate models. Let's say I've tried different ones and I evaluate them. So based on the evaluation, so probably I use RMSE, MAE, AIC, BIC. I'm going to select the best model in terms of its performance. And based on the model, I can make forecast forward. I can make, so for instance, now if you observe this, you see that we are making a forecast. So from where you have your blue line to the end, you have what? Your forecast. And you see the shaded points accounting for the uncertainty, that is both the 80% confidence interval and 95% confidence interval. So I think I have to stop there. Then let's see if I can take question.
Let's appreciate our facilitator. So we have been introduced to time series analysis, and then I think we have the background knowledge now. How many of us are participating for the practical class? You want to lay your hands on you want to use R to, you want to generate this plot yourself. So we'll be having the practical class. So then before that, if there are any questions, I don't know if anyone is having any question.
Question?
Okay, I will just take the numbering ones. Okay, one. Just one person. So we have been introduced on why do we have to decompose our data and all of those things. So how do you bring those things into your area? How do you decompose your data? Maybe you're in health system, you're in finance system. How do you bring your data in? I think when the lecture was going on, that should be the area whereby you'll be thinking, oh, how do I bring my data in? So if I decompose my data, so what am I going to see? Am I going to see the trend, the seasonality, and all of those things? So I think, I don't know if there are still more questions. So just only one question. All right, so I'll just take the question.
So thank you very much for the detailed lecture.
Yes, ma'am.
I just want to ask a question about when you talk about time series, you are talking about, I think financial data, example is maybe stock price collected over a period of time, right?
Yes.
So now, when modeling such cases, we normally take the log returns of the stock price, you know, and it has some reasons why financial mathematicians do that. It has some mathematical properties, especially when it's believed that the geometric Brownian motion process is driven by the log returns.
Okay.
So, and other properties too. It's also used for asset pricing, option pricing, and the rest. So now, bringing it to time series,
yes,
before you check for seasonality and the other, the trend and those things, do we need to get the log returns before you apply it to this kind of time series models?
Okay, thank you very much.
That's my question.
Okay, thank you very much, ma'am. There are reasons why we call it data transformation. So it's not just only log that we have. Sometimes we could square. I will give reasons, particularly in where I working very close with, which is epidemiology. So for instance, we could take the, is it square root now or square? Okay, square root, yes. For instance now, if we don't do such data transformation many times, oftentimes when we are taking our forecast and it's accounting for uncertainty, we might be having our uncertainty towards negative, which is unrealistic in terms of our forecast, in terms of reporting our forecast. Can imagine we're having, let's say we have a point estimate of, for the forecast, we have a point estimate of 10 for a particular month, and the uncertainty is from, let's say, -2 to, let's say, I'm just giving an hypothetical example. The uncertainty is from -2 to, let's say, 15, but the point estimate is this. So we can't be given reporting an estimate which biologically is not meaningful in terms of, you can't have a negative minus case of, so which is one of the reasons why we do data transformation like that. So I want to believe that's also applicable to finance also as well. Did I answer your question? All right.
There's still another.
All right. So
one very strong reason for that is that when you have when you want to do some comparison, you know, like time series analysis, you can use it to handle time series at different spatial level. maybe you are comparing financial stock exchange time series data of different location. And then you want to do comparison. You understand? So you find out that now, when you look at the least value for this particular time series may not be the least value for this other time series of a particular location. So for you to put them at the same least value, the same upper value, upper and lower bound, the same upper bound. So that's one very important reason, so that it will be easy for you to do comparison. You want to compare the two together. Do you understand me now? So that's very much important, because like most of them are very noisy, and you find out that they are different. The maximum value of this particular one is different from the other one. So, and you need to linearize for them to be at the same level that you can compare, because you cannot compare like different time series value of different locations that does not have the same the same bounds. You understand? You can't compare them, because I mean, so the reason, one of the reasons, apart from denoising and linearizing and all of that, is for good comparison. Thank you.
Thank you, sir.
There's another question.
Well done, sir. I just want to ask that, is data decomposition and data cleaning, are they the same?
No, they are not the same. They are not the same. Okay? They are not the same. So it's just like data cleaning is like pre-processing. You are pre-processing your data before you carry out your analysis. So you have to have clean your data. Are there missing values, outliers, and stuff like that? That has to do. Are they in the same unit? Is there uniformity? So that's what data cleaning helps you to do. So it is when you have cleaned your data, then you can carry out a proper analysis as to what you want to do. Okay? All right. So any. Okay. All right.
Okay, this person says, thank you very much for the fluent delivery. Please, how will you build a spatio-temporal time series model for malaria incidence? That account for seasonality over the spatial leakage.
That's a lot. Please, can you let me read the question again? So that's fine.
All right, so dispersion, climate lag effects.
Okay. I'm going to, from what I understand from the question. So already in time series model, already I think you see that I mentioned the concept of lag in terms of lag. Then also majorly when it comes to data and we are trying to focus, there are different domain. So there is that I know of. I don't know when it comes to spatial temporal. There is time domain, which is what you are looking at. You are looking at that in time. There is frequency domain. You are looking at, based on your data, what are the frequencies you can observe. Then there is that merge, that is the time and frequency domain. So, and I don't know if Prof can help respond to that.
As in terms of time series data for different locations, like geographical locations. That's what it's talking about. So it's talking about space and then time series data. So the temporal there is the time series data that you have. The space there is that you have a time series data, maybe that cover states in Southwest. Take for instance, different states in Southwest. We have how many states in Southwest? 6 states, right?
Yeah,
so the time series data is temporal, because it's talking about the time trends, right? And then the space are the
Location.
Lagos states, Ogun State, Ekiti State, all of that. Now, in such data, you'll find out that, and that's longitudinal. So you find out that, what's it called? Possibility of having some of those things, the variance, like over dispersion and that you was talking about. I mean, it's very possible. That was why I was saying that if you have such data set, the first thing to do is to test for normality, normal distribution. Check the distribution of that data before you even subject it to time series decomposition, before you now say you are doing it. And then one good thing to do also is to do data transformation. Now, if you don't do data transformation, now if you have data from all those different states, you cannot do comparison because they are not on the same scale. So you have to scale them by normalizing them so that they, if it is square root, if it is box, the other one, and then other log transformation, you should be able to put them at the same scale. So if I have Lagos states, and Lagos state, the peak is 1,000, right? Normal number of cases, 1,000. And then the trough, that is the least value, the least is maybe 10. And then I have Ogun State, the top is 10,000. And then the least is 1,000. Can you compare? You can't do good comparison. So the only way to do that is to scale by transforming each of those data. You transform all of them. Once you transform all of them, you have already do a kind of denoising. You understand? Normalizing the data. So when you do that, you can you can first of all do data transformation before you carry out time series analysis on that data. That's the answer to that question.
Okay, the last question from A. Can we do a time series analysis for categorical data?
No, based on the definition of what a time series data is. It's ordered in time. An observation could be entity, individual. So it does not fall to the category of, it has to be numerical. So it does not fall to the category of what we can call a time series data. So it is on time series data, you can implement time series model. So there could be other analysis you can do on categorical data, but not time series.
Other analysis can be done because most time you have it at an instant of time.
Yeah.
Maybe you are collecting what's it called? Questionnaire. You understand? You have a questionnaire, and then you eventually convert. For you to use it, you have to convert it to numerics. That is called coding. Coding. Yeah. Those days when I used to use SPSS, you convert maybe your yes to be 1, and then your no to be 0. And then you do all those stuff. Thank you.
Once again, let's appreciate our facilitator.
Thank you. Thank you. Thank you.
Okay. Thank you, Mr. Sampson. So we'll be having our fellowship today. Yes. By what time? Okay. By what time? All right, so for our Christian brethren, our fellowship, Bible study will be starting by 5:30. So when it's 5:30, let's converge at our our usual place where we used to meet for fellowship. So now, let's see. Okay, now we'll be going for our group meetings. So I think we need to converge at our group spots on time so that we'll be able to do something before that 5:30. So thank you. We can progress our group meeting. Thank you very much.